All right, have you ever heard of Sir Isaac Newton and the three laws of motion? Well, he's very famous. You need to know about him. He was not only a scientist, he was a mathematician and an astronomer. He liked to study the stars. And he lived in England around the 1600s, early 1700s. And he's considered one of the most important scientists in history. During his lifetime, he developed the theory of gravity. He discovered gravity. And there was a legend that he was sitting underneath an apple tree. And when he saw an apple fall from the tree, then he figured out, there must be a force pulling things down towards the ground. And so that's what gave him the inspiration. But we aren't sure if that's actually what happened, but that's the legend. So whenever you see a scientist holding an apple, you're probably looking at Sir Isaac Newton. And he studied gravity and the laws of motion, and all of that became the basics of what we know as physics. If people study physics, it's all based on the things that he came up with. And he came up with a new type of math called calculus that's not so new anymore. It's been around a long time. And he also invented the reflecting telescope that is still used today. So lots of things are attributed to Sir Isaac Newton. And here are his three most important laws of motion. These are the things that he discovered. Law number one, an object in motion will stay in motion. An object at rest will stay at rest. And if you think about it, if you look at something like a stapler sitting on a tabletop or a vase, if nothing moves it, it will stay there. And then if something is rolling down a hill, nothing's going to stop it unless it gets in the way. Something actually does stop it. Either, it bumps into something, gravity, friction, something like that. We'll look more at that as we go along. Law number two. The greater the mass of an object, the more force it will take to accelerate the object. So in other words, if there's a big, huge boulder sitting at the top of a cliff, all right, that would be a massive object. And it will take a lot more force to push it off the cliff than it would be a smaller, a boulder of, a rock that was much smaller in mass. So that's kind of like common sense, but he thought of that. And number three, for every action, there's an equal and opposite action. Okay, and we're going to look at that with some bumper balls, human bumper balls, coming up in a cute video. So let's look more carefully at these laws. Law number one, an object in motion will stay in motion. An object at rest will stay at rest. So his first law, here's a soccer ball, and it's just going to sit there unless it is acted upon by a force, like a foot. And then it's going to stay in motion unless it's acted on by an unbalanced force, which would be maybe the net or gravity pulling it down towards the ground, something like that. So an object will stay at rest, and an object in motion will stay in motion unless something's acted upon. Okay, law number two. The greater the mass of an object, the more force it will take to accelerate it. All right, so to get the wagon to accelerate, you have to you have to apply a lot of force, okay, to pull it. Well, if it got heavier, what if you had more of those things? It's going to take a lot more force to pull that heavier wagon than it would be with just one object on it. And I love this right here. For every action, there is an equal and opposite action. I have this little gadget right here in my classroom, and I will pull it out as soon as this video is over, and we'll take a look at Newton's law number three, and it's called a Newton's cradle. That's the name of the toy. It's not really a toy. It's an interesting little gadget, but it's called Newton's cradle, and it is proving that for every action there is an equal and opposite action. So if these two are pushing on each other equally, the carts are going to pull apart, separate from where their feet are pushing against them, equally. Okay, and all right, watch, this is another one. If you're standing on the front of a boat, okay, and if you push off of it so that you can jump out into the water, the boat, for the same amount of force that you're going to put into your own action going forward, the same amount of force is going to push that boat backwards. It's an equal and opposite reaction. Okay, so let's take a look at Newton's law number 1 in this video clip.
These drivers lost control at very high speeds. The result was tragic for one driver and fortunate for the others. But why? What made the difference between walking away and being carried away? The answer can be found in some of the most basic laws of the physical universe. Hi, my name is Griff Jones. I teach high school physics. And behind me is the Insurance Institute for Highway Safety's Vehicle Research Center. It's a fascinating place where research engineers assess the crash performance of vehicles by running tests, and where they evaluate new technologies to prevent injuries, like this state-of-the-art head protection system. What's exciting for me is that this is a laboratory of practical applications in the subject I teach. And because they're set up here to crash cars and analyze those crashes, this research center provides a perfect venue for illustrating the physical laws that govern the outcome of car crashes. So follow me, and for the next few minutes, I'll take you behind the scenes where we can explore the basic science behind vehicle crashes. Let's learn about car crashes and physics. Why'd this dummy get left behind? It's called inertia, the property of matter that causes it to resist any change in its state of motion. Galileo introduced the concept in the late 1500s, and almost 100 years later, Newton used this idea to formulate his first law of motion, the law of inertia. It's why the dummy fell off the back of the truck. It was at rest, and it wanted to remain at rest. That's inertia. It's the same property that keeps the china on the table as you pull the tablecloth out from under it. Now what about a body in motion? Am I a body in motion? You bet I am. I'm moving 35 miles per hour. But from one perspective, it may not look like I'm moving at all, because in relationship to the passenger compartment, my position isn't changing. But if you look at me from the outside, you can see that I'm moving at the same speed as the vehicle, in this case about 35 miles per hour. And if Newton was right, and we know he was, I'm going to keep on moving at the same speed until an external force acts on me. Now, what does this mean to occupants of a moving vehicle? Watch this. See how the car and the crash test dummy are traveling at the same speed? Now watch what happens when the car crashes into the barrier. The front end of the car is crushing and absorbing energy, which slows down the rest of the car. But the dummy inside keeps on moving at its original speed until it strikes the steering wheel and windshield. This is because the dummy is a body in motion traveling at 35 miles per hour and remains traveling 35 miles per hour in the same direction until acted upon by an outside force. In this case, it's the impact with the steering wheel and windshield that applies the force that overcomes the dummy's inertia. Inertia is one reason that seatbelts are so important. Inertia is one reason that you want to be tied to the vehicle during a crash. If you're wearing your seatbelt, you slow down with the occupant compartment as the vehicle's front end does its job of crumpling and absorbing crash forces. Later, we'll talk about how some vehicles' front ends, or crumple zones, do a better job of absorbing crash forces than others.
Okay, so going back to PowerPoint. Okay, so here's another one about football. Let's watch the football.
In this video, we're going to talk about Newton's law of motion. And there's three.
Whether it's a running back breaking through the secondary or a wide receiver on a foot race for the end zone, most offensive players in the NFL have a single goal in mind: to get downfield as far and as fast as possible.
We're thinking, wow, I've got to get from A to B within a certain time frame, and I can't let this guy throw me off track. So it's kind of like a chess match at that point in time. It's the battle to see who's the toughest.
Defenders, on the other hand, have a different goal: to stand in the way of the offensive player and stop his forward progress.
When you're coming in and making a tackle, you've got to come in and you've got to stop him right there on the dime.
Who wins this epic battle between the ball carrier and the defender? Newton's first law of motion helps supply some answers.
Newton's first law says that if an object is at rest, it requires an unbalanced force to make it not be at rest. Or similarly, if an object is in motion, it tends to stay in motion in a straight line at a constant velocity unless an unbalanced force acts on it.
In football, we see unbalanced forces whenever one player exerts a force on another and causes him to change his direction and/or speed.
So imagine that a quarterback is just taking a snap from the center, and a lineman gets free from the opposing team and is coming from the other side, and when they collide, you can see an unbalanced force acting on the quarterback, driving him across the field in the direction of the charging lineman. That's about as unbalanced as it gets.
In physics, a player's natural resistance to that unbalanced force is something called inertia.
On the football field, you can think about inertia as being a running back who's already in motion, doesn't want to change the fact that it's already in motion. So it's going to take some external unbalanced force, i.e. a defensive player, to stop that running back.
Consider former New Orleans Saints running back Deuce McAllister, who at 6'1", 231 pounds, used his inertia when running to make him hard to tackle.
The size of the player is important to the concept of inertia because higher mass means more inertia.
But a player's mass is different from his weight. Mass is a measure of how much matter an object has, while weight is a measure of how strongly an object's mass is attracted by gravity.
So, for example, a body on Earth would have the same mass as that body on the moon, but it would weigh less on the moon because gravity is less on the moon than it is on Earth.
NFL players with more mass have more inertia and are harder to move off their path. This concept even works on a quarterback sneak, when a quarterback uses the combined mass of his entire offensive line to gain a yard or two.
If you've got an offensive line that can overpower the defensive line, that's just what you do. You get on their hip and you just fall. And you just ride that wave forward.
In the NFL, whenever players go head-to-head, it's Newton's first law of motion that helps determine who will win the battle of the gridiron.
Okay, so I think we're going to stop there for today, but then we are going to take a look at Newton's law number 3 when we pick back up in our next video.